So hello again. Tonight's topic is dark accelerating objects. These are things that are hard to see, and how fast they're going and what direction they're going changes. And there's a lot of speculation as to maybe these are actually technological craft that are manned by individuals from outside of our solar system. There's a lot of people that tend to believe that, but I saw something this week that I'm doubting about that. And the source of it is, yep, I watched another YouTube video. It's going to be a fairly short one compared to last week's couple of hours. Another StarTalk YouTube video, this one called Dark Comets, or their investigation into Oumuamua, the asteroid slash comet. There was a visitor just passing through our solar system. Oumuamua is Hawaiian for scout. So it was like a scout craft passing through. The presentation that I watched on StarTalk kind of started with Oumuamua, and then they moved over into, well, comets that can't be identified as comets, and it's because we can't see tails on them, and they're dark, labeled it, this one postgraduate scientist labeled it as dark comets. But the interesting part of his presentation on StarTalk was sources of minute propulsion that have a collective effect that change the orbits of things. And there's two different flavors of that. There's one for inside the solar system and one for when you're outside the solar system in the interstellar cosmic wind. So here's Oumuamua, the picture at the top right. That's an artistic rendering. It looks like a giant turdsicle. That is not a picture. That's not even like a color mapped infrared picture. It's just, that's some artist's idea of it. The thing in the middle, all the white dashes and dashes, dots and dashes, the little green circle in the middle, that little one white dot, that's actually a telescope image tracking this object. So the object is moving different than the background stars. And if you've ever seen people taking pictures of comets that are long duration exposures, you can have the telescope lock on to the object and the stars move, or you can lock on to the stars and then have the object streak. So in this case, they locked onto this object, and the dots in the background are the stars. The interesting thing is they're not purely streaks. They're dots with gaps, which says the collective images of this moving object were not continuous. They were like, take a sample, pause for a moment, store it, take a sample. That's where you see dot, 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 dot. And then they went away for a while and you see a gap. And then you see more dots. So it was not just one long duration image. It was a stack of images where the telescope is tracking Oumuamua. And then the actual picture of it. We have no visual images of it. We have a radar image of it. So what you're seeing there, all the little pixelated gray is a radar image, which is why it's not in color, of the object. And it kind of looks elongated, and it actually moves. So it rotates and revolves as it's going along in space. So how do we know it came from outside? Well, if something is orbiting the sun, even at a very long distance, like things out in the Kuiper Belt, if you take data points and observations of their orbit, you'll find that that becomes a segment or a section of a parabola, which is part of its ellipsoidal orbit. So if you have an object that's going from the asteroid belt in behind the sun, coming back out again and going out to the asteroid belt, a short duration comet, then it will make an ellipse. But if you just look at a section of its track, it makes a parabolic section. If something comes in from outside the solar system that originally was orbiting something like a star or a planet in another solar system, when it was kicked out, it very much broke that ellipsoidal shape. So it's as if it started down one side and then just kept going. And this shape forms a hyperbolic section, or a hyperbola. Not hyperbole, that's something different. it forms a hyperbolic section. And by tracking the path of this object, that's how we knew it came from outside. It isn't just like a really, really, Kuiper Belt deep asteroid or comet. That's how we knew it came from outside. But how did we know whether it was an asteroid or a comet? That's where the interesting part started. But put a push pin in that, because we have another thing to talk about, which is the thing that really raises the, hey, how does it do that kind of stuff? And that's acceleration. The objects that are in orbit around the sun have an orbit, and the orbit has orbital parameters. And those orbital parameters change over time. And the reason why they change over time is not because they keep flying by like a Jupiter or something. It's because the solar wind encounters these objects and does one of my favorite physics things. It induces radiation reflection pressure or radiation pressure on the object, which if it's getting it on the side, it changes the orbit laterally. If it's getting it head on, it can slow it down. If it's moving away, it can speed it up. It's just a little tiny oomph. And if you don't watch all these near Earth objects on a recurring basis, very periodically, they might change their orbit and go from not a problem to it's going to be a problem in 20 years. So that's why they have to keep looking at these near Earth objects. They've mapped thousands of them. How come they keep looking? Well, there could be ones that they haven't seen, and there could be ones that have slightly changed their orbit from safe to not so safe. As it turns out, there's another thing that can happen because these are very small, not propulsion, but more like push changes. So if you have a comet and it comes in towards the sun, it will grow a tail. And as it gets closer to the sun, the tail gets longer. And then as it swings around the back of the sun, the tail swings with it. And then as it goes away from the sun, the tail changes. It goes in front of it because that's where the solar wind radiation is pushing the particles in the gas. But once it gets out beyond a certain distance, the solar wind is no longer strong enough to make the tail occur. Something coming in from the Oort cloud or the asteroid belt can look like an asteroid because it doesn't have a tail. And then it gets close enough to the sun that, oh, look, it's got a tail now. Must be a comet, not an asteroid. So when they see it out there, looks like an asteroid, no tail. As it comes in, oh, looky, it's growing a tail. So it must be a comet. When you look at the catalog of minor planets, this is why sometimes you'll see things that the first letter is a C for a comet or a P for a planetary body. And you'll see it like, well, we thought it was a P, but now that it's making a tail, we're going to change it to a C. So you see things flipping. The only reason why it forms a tail, it has a lot of stuff on the outside of it called volatiles. And these are materials that when the solar radiation hits them, they evaporate, create dust clouds, and these things are just referred to as volatiles. Now, in regular chemistry, you'd say a volatile is something that explodes, right? No. In astrophysics and comet studies, a volatile is just something that when the solar radiation hits it, it kind of spews out, makes a tail, evaporates. So they just refer to it as volatile outgassing. If you have these things, but you're in the asteroid belt and you never get close enough to the sun, you can be a comet that we thought all along was an asteroid because we never saw it grow a tail because it's stuck out in the asteroid belt too far from the sun. Or as I like to think of it as, a square is a rectangle, but not all rectangles are squares. So how do you get a dark comet? If these hydroxyls, the waters and the alcohols and such, are sufficient to form a tail, but they're far enough out that they never get exposed to enough solar wind to form a tail, how do you know that they're a comet and not an asteroid, not a dry rock? Well, as it turns out, if you've ever listened to Helen's explanations about comets, dark carbon is a lot of what a comet is. So they can be very dark. So when it doesn't have a tail, it's very dark visually. it's very hard to do a spectral analysis of the chemistry of a dark comet because you just don't get all the data you need because the light coming off of it, reflecting off of it, is so dim. But if you look at it in infrared, even if the light coming off of it is not enough to make a tail, it's enough for you to pick up via spectroscopic analysis the chemical structure of what's on the outside of this thing. So you can see from that, from the spectral analysis, whether this thing has stuff on the outside that would make it a comet if it was closer to the sun, or it's just a dry rock. Even if you put it closer to the sun, you're not really going to get any distinguishable tail off of it. That's how you tell. You switch your viewing from visual to infrared, and then you do a spectroscopic analysis of the light, dim though it is, coming off of it, and you have to use a giant telescope, and the James Webb Space Telescope is the right tool for that. But remember, if this thing is going in towards the sun and it doesn't have a tail yet, the Webb telescope is not going to be looking in that direction. We'd be blinded and destroyed by the sun. So it's got to be when it's out there in the asteroid belt, and you can look at it out there with the sun at your back, so to speak. So what about this interstellar cosmic wind? We know about the photons and particles coming off of the sun. That's the solar wind from the sun. Turns out when you have a galaxy, that solar wind material, you can think of it as there's billions of stars out there, and they're all producing their own wind. And there are very energetic things like neutron stars and black holes and all these very energetic things that are just spewing particles, photons, out into the interstellar void. So as it turns out, the interstellar void, the space between solar systems, actually has very much higher energy particles. They're hard X-rays and gamma versus the soft X-rays with a lot less gamma within the solar system. Daryl Seligman, who's an astrophysicist, and he's employed by the U.S. National Science Foundation as a postdoctoral fellow, and he's got some folks working for him, and he's got them off looking at not just the radiation reflection pressure of the interstellar wind, because it's so much higher energy. They're looking at it as, okay, so if I happen to have this interstellar comet that has these hydroxyl molecules that are coating the outside of it, will the higher energy split the molecules? And if the higher energy will split the molecules, one of the atoms you'll have is hydrogen. And it doesn't take that much energy to make hydrogen ionized. And if you ionize the hydrogen and the ions want to leave the interstellar object, it creates an ion propulsion. Not massive, maybe only millinewtons in scale, but now you have two sources of push associated with these interstellar objects. You have one that, cosmic wind pushing on it, and then you have its own propulsion source in the form of like a little ion propulsion jet from the high energy radiation hitting it, splitting the molecules, ionizing the hydrogen, and then the hydrogen electrons, the ions, act as a little jet. So it can accelerate it. So it can be pushed in a direction and also accelerated. So it will change its direction and velocity. So that's the idea is, although it's minuscule per particle, per ion, collectively, it's much larger than that. And so it's digitally measurable. And acceleration can be an acceleration or deceleration, but they just refer to acceleration as being positive or negative. So if we have an object that comes from outside our solar system and it's under the influence of interstellar winds, then it can be having two sources of acceleration. One is the radiation reflection pressure from the cosmic wind. And the second one is the breaking apart of the materials and producing the ion propulsion effect. So as it's going through interstellar space, it's moving in a particular direction at a particular speed. And then as it enters our solar system, it gets robbed of the cosmic wind because the sun basically acts as a giant defense shield around our solar system to protect us from the interstellar wind. So it loses that. Well, when something is under steady source of propulsion and you take it away, and you now encounter a denser environment like our solar system, you're going to slow down. So here we have this object that was traversing the galaxy at a certain speed in a certain direction, and it encounters the solar wind of our solar system and removal of the cosmic wind. It changes speed, it decelerates, and it changes course. Because if the cosmic wind was in a certain direction for it, and now it's under the solar wind, it's going to change its direction. So this object went from going fast in one direction to slowing down and changing course. And it stayed that course through our solar system. And as soon as it exited the solar system, it sped back up again and it slightly changed course. So it looked like it's a probe from another star system giving us a look over. So it entered our star system, slowed down, examined us, and then when it got done with its observations, it sped back up onto the next star system. So this is kind of what people were thinking was, it's not just a natural phenomenon, alien technology. Turns out it's not. So that's basically what you've got is Oumuamua arrived in the solar system, slowed down, changed direction, and then as it had enough momentum to carry it out of our solar system, it sped back up and got back up on its original course. Seems plausible to me. And that's what this astrophysicist was postulating, was he's got a reason why Oumuamua slowed down, changed direction, and then as it left, it sped back up and got back on its original course. But then they went in and started discussing, well, how did we even see this in the first place? And it turns out Oumuamua is slow and somewhat reflective. It's not as dark as we thought it was. Well, if it was darker, we might see it in infrared if we knew to look for it. But you remember when it's taking the images and you saw like dot, 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 gap, dot, 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 gap? Well, those are the periods when we weren't looking. If this object were moving much faster, we wouldn't have seen it at all. Because if it's moving much faster, then if we look in a particular field of view with a telescope from night to night, we'll no longer be able to do the delta, the peak from one image to the next to see the white dot move. It'll be a white dot in this image, and then it's gone. Or you didn't expose it long enough, and there is no white dot at all. It's just like zip going through. Doesn't even get recorded. If an object is not sufficiently reflective for us to even see the dot, or if it's moving through the image so fast and the exposure is so short, we don't even catch it, there could be objects moving through our solar system right now that we are unable to observe, and hopefully they're not going to cause us any problems, but we won't know. But how would we observe them? Well, switch out of periodic camera mode, even in infrared, and switch to radar. Think of an airport. Think of an aircraft carrier. They have continuous radar. Nowadays, it's digital, so there's no moving parts. It's just phased array radar. But that's how you spot things that you would otherwise miss, because you're always looking. 360, 24/7, you're always looking. But we need it in two forms. The close-in stuff, instead of having satellites out at geostationary orbit that are looking inward or communicating inward, you want them communicating inward, but looking in radar outward. So they're scanning things that might only be 1,000,000 miles away or closer, because the time transfer from the radar transmitter to bounce off the object and to come back, you'd like to keep that to roughly a second. Because you go any further and you have to transmit the radar pulse and then come back later and receive it. for the deep space stuff, for the stuff that's out in our solar system, and we want to watch it arriving from millions of miles away, NASA has this thing called the Goldstone Solar System Radar. Back when we had this thing in Puerto Rico called Arecibo, we would use that. But there was only one of them. Goldstone is also only one of them. What we need is a network of Earth-based, purpose-built solar system radar. So you have them, around the globe, and they're constantly just transmitting a signal out. And then as the Earth rotates, the next antenna will pick up the received signal. So it may be that, you send your radar pulse out, it bounces off of something 6 hours later, and then 12 hours later, you need to pick up the received signal. So it has to be continuous. Like, I'll send it out now, and on my next antenna around, I'll pick it up. But if the objects are at different distances, then you have to be constantly listening for your reflected signal, because you don't know what distance it's going to be at. And the light travel time is such that it could take hours to days. Remember, the light travel time out to like Voyager, I think is 16 hours or something like that. It's a good portion of a day. So if you say, hey, are you there? You have to wait 32 hours before it'll get it and respond and then send it back to you and arrives at Earth again. Same sort of thing with the radar. So what we need is an Earth short distance scanner radar and an Earth long distance scanner radar. And this is not the kind of thing that NASA does well. It's the kind of thing that the Department of Defense does well. They have a lot of experience with radars and such. So give some funding money to the DoD to do this. Maybe encourage it worldwide, because it's a planetary defense network. So if these large bodies are passing through our solar system, what happens to them? Well, they can either zip through and not hit anything, or if you've ever watched sun-grazing comets, they can try and go around the sun and not have enough velocity to carry through the other way. And so the comet just does a nosedive into the sun. Well, when these objects are coming in from interstellar space, they can do the same thing. They can go too close to the sun and burn up in the sun. Or they can be too close to one of the Jovian planets, Jupiter, Saturn, Uranus, or Neptune, which have large gravity fields, and they can get too close and into those large planets. But since their outer atmosphere is mostly gaseous, we probably wouldn't even notice it, especially if it happened on the far side of the planet. There might be a bruise, and we've actually seen this where Jupiter would rotate around, and we go, oh, look, there's the yellow-brown spot on Jupiter. Something must have hit it, but it was round on the dark side that we weren't able to see when it impacted it. So it's just like, boop, into the atmosphere, never to be seen again, but it left a bruise on the atmosphere that lasts a few days. Or you can have captures. These things coming from interstellar space into our solar system can suddenly find themselves in orbit, in a nice captured safe orbit around large planets in our solar system. Now, why the large planets? Why not Earth? How come Earth doesn't capture them? Because Earth is much smaller, and Earth's gravitational field is also much smaller. If someday, while we're exploring some of the countless moons of Jupiter or Saturn, Uranus, and Neptune, we encounter one and we look at the water ice on it, and we find that the particular hydrogen isotope percentages of that water ice are different than they are on Earth, then this water did not originate from the same place that Earth's water originated from, which means that may not be a natural moon of Jupiter. That may be an interstellar comet that got captured by Jupiter's gravity. But we won't know until we start taking samples out there. But if we do find one, it's just like an interstellar tourist that overstayed their welcome at Jupiter and got trapped. So in summary, something that is initially unexplained can exist, but then through observations and hypothesis, you arrive at a possible explanation. You then do observations, have other people do observations, repeat them, verify them, and now you can verify your hypothesis as to, is that really what's happening? And then you have people review your peer review your scientific research, your report out, and if they go, yep, makes sense to me, then that's how you come to a conclusion. It's not like that must be aliens. It's just simply science. Maybe there are things passing through our solar system that we just can't see because they're moving too fast or they're too dim, and they wind up crashing into planets or crashing into the sun. But if something big and dark and very fast is headed our way, we might not notice it until it's like inside the orbit of the moon, when it's close enough that we can now see it easily. When it's further away, or if it's coming in from the direction of the sun, might not be able to see it. Only way to find it, keep looking. And then links, including the StarTalk link, couple links on Oumuamua. Okay. Shorter and no math formulas, physics, but no physics formulas. No numerical calculations.
Formulas.
Yep. Ought to go well when I post it on YouTube for the public.
Well, these lonesome travelers can be pretty scary for our poor little planet if it hits us.
Well, luckily we're small and the universe is big. And we've got larger things like the sun, Jupiter, Saturn, Uranus, and Neptune with very large gravity fields helping us out.
Yeah. Mm-hmm.
But the interesting question that came up during the StarTalk presentation was, does our solar system lose stuff? Does stuff get kicked out? Well, it doesn't anymore, but back during the early days when like Jupiter and Saturn were moving from the inner solar system to the outer solar system, there was a lot of stuff being scattered out there. So we could actually have been sending thousands of interstellar visitors to other star systems billions of years ago. Any comments or questions?
No. Very good. Interesting.
Okay. Then I'll stop recording.